okay to start now, Jan?
Yes, now we can
Yeah,
start.
okay, thanks. Thanks very much, Jan, for the introduction, and thanks to the organisers for the invitation to talk. Yeah, I'm sorry not to be with you, missing that beautiful scenery. Yeah, so I'm Julie Staunton. I'm from the University of Warwick in the UK. I'm in the physics department here. I'd just like to also mention that I'm involved with this postgraduate training centre at Warwick that specialises in modelling of heterogeneous systems. Essentially, it's a centre for computational materials modelling. Anyway, so as Jan said, I'm going to talk today about relativistic effects in condensed matter and how multiple scattering theory is used to describe them. The applications I'm going to concentrate on will be primarily towards magnetic properties and specifically, again, as mentioned earlier, magnetic anisotropy and where that comes from the relativistic effects. I thought just before I get stuck into the multiple scattering theory and the relativistic aspects, I'd just like to make some preliminary remarks just to set the scene. Just take us back to just think about magnetism in condensed matter. Obviously, there's the exchange interactions, which are dominant, and they're coming from the fact that the quantum mechanical wave function describing the many electrons in a material must be overall antisymmetric, meaning it's consistent with the Pauli exclusion principle. And that with the spin degrees of freedom, it generates the magnetic, the basis of magnetic effects in materials. And one can see where the Heisenberg interaction comes from, some effective spin interaction comes from for insulators, from that sort of analysis. And then in a density functional theory prescription of materials properties, you have the spin polarized electronic bands in some metals. However, you can see from these first two bullet points that there's nothing there that links these electron spins to any spatial direction. And that's where we go on to include relativistic effects, particularly spin-orbit coupling, to do that. And that's actually absolutely crucial for understanding many aspects of magnetic properties. Just, for example, what is the easy axis for the magnetization in the system? How magnetically hard, how robust is the magnetism against fluctuating fields, etc.? What's the nature of the domain wall structure in a material? And of particular interest, I would think to this summer school, transport properties for spintronics applications, etc. Anomalous Hall effects, spin-orbit torque, and so on. Topological materials, what are the influence, what's the ramifications of spin-orbit coupling in different structured materials, and magnetic nanostructures, and there's a lot of work now on looking at different sorts of recording ideas involving skyrmion structures. Okay, so that's by way of an introduction. So just before I talk about the more detailed aspects of the scattering, multiple scattering, again, I just like to concentrate on how one sets about modelling magnets at relatively long length scales. So this is where there's the free energy of a magnet is written down, and a key contribution to that expression, as you can see here in red, is a term which I've just labelled as uniaxial, an anisotropy term. And this is the piece that one has to include when you're trying to model materials properties, magnetic materials properties, to capture these important effects that determine many aspects. And as I say, from a fundamental level, it's derived from the spin-orbit coupling of the electrons. Just before I move on, just to complete the picture, the other terms, the first term in this free energy expression, that's largely coming from the exchange interactions. That's giving the energy cost of modulating the magnetic structure through the material. So as you can sort of tilt the magnetization throughout the material, you get this energy cost. There's the interaction with an applied magnetic field. There's also a piece that's dependent on the shape of the material, so the shape anisotropy. So the dipole-dipole interaction comes in there. But for the focus of this talk, I'll be sort of digging into what drives the magnitude and the nature of that anisotropy term. And as I said, it's fundamental to understanding magnetic properties. It tells a large term means that you're describing a permanent magnet. The magnet is very hard. Sometimes it's suitable to engineer materials which have small anisotropy, so it's very magnetically soft. The materials have high permeability. If you're looking at nanoparticles, a large U term, anisotropy term, means that the magnetic information you might want to store by the orientation of the magnetization in that magnetic particle will be particularly stable, so i.e. the blocking temperatures will be high. So, as I said, this property is linked to the spin-orbit coupling, so that means it's going to be big for materials which have got elements with high atomic number. And also, if I have time, I'll say a little bit about this towards the end. It also has a strong temperature dependence, and because of its nature, is heavily tied to the composition of the material and its structure. Okay, so let's just move on to think of one source of this term. This is a famous one. It's coming from crystal field effects. So very often, if you is looking to find a good permanent magnet, then you would involve one that had some amount of a rare earth element in it, something like samarium or neodymium or whatever. And here the main contribution to the anisotropy of such a magnet comes from the rare earth. And this is because from its localized F-electron configurations. So pretty much you can understand these localized F-electron state configurations from Hund's first and second rules. So you'd maximize the spin, and you'd also maximize the orbital angular momentum. And so we'll have these pictures here that I've shown on the slide of the distributions of the wave functions of the charge distributions. And then if we're thinking about these states, then the spin-orbit coupling will cause this charge distribution to be dragged around with the spin as the magnetization direction of the system is altered. Now, as this F-electron charge distribution is dragged around, there's an electrostatic energy cost from the surrounding charges in the material, namely the crystal field. And that's, in a nutshell, what generates a significant so-called on-site magnetic anisotropy that comes along with these rare earth atoms. Now, if we want to get on to looking at the origins of these anisotropy effects formally, from this kind of point of view that you're looking at very much in the summer school, you want to be able to consider it from sort of first principles. So we have this question of how to deal with all the many interacting electrons in a bulk system. And if at the outset we want to include these relativistic effects properly, then the way to look at that is to take the full-blown many-body quantum electrodynamics into account. Now, in the early days of density functional theory, back in the 70s and 80s, soon after, not long after Sham, Hohenberg and Kohn developed their density functional theory, people thought about generalizing it to include relativistic effects, and there was seminal papers by Rajagopal, Alan MacDonald, Vosco, and other people who developed this approach. And what they set out was now that, sort of analogous to the density functional theory that you're probably familiar with, you have a ground state energy for the interacting electron system, but in this case it's a functional of the so-called forecurrent, or in other words, the charge density of the electrons and the current density. And there's an external field that one considers, and that has a scalar part and also a vector part. And just in the same way that the arguments for regular density functional proceeds, you would then minimize this functional to produce the appropriate ground state energy and current density. So that's all written down. And so that this minimization would be carried out exactly the same way as Kohn-Sham set out, but in this case you'd solve a single electron Kohn-Sham-Dirac equation rather than a Kohn-Sham-Schrödinger equation. A single relativistic electron moving in an effective field set up by all the other electrons. Typically, and certainly pretty much all the work I've done, one makes a further approximation on this, and one uses the so-called Gordon decomposition of the current, and so one neglects the sort of diamagnetic contribution to the current and focuses on the piece of the current that's coming from the spin polarized nature of the density, the electron density. And so one then ends up with, again, an energy functional, which is now formally a function of the charge density, electronic charge density, and the magnetization density. And then, as I said, one then proceeds to minimize this with appropriate approximations for the exchange and correlation, etc., by solving a single electron Dirac equation moving in effective fields. So that's the fundamental starting point. And then once one has a handle on this energy, then one can consider what happens when the overall magnetization or magnetization within the system is varying its orientation. And that's, as we see, is driven by the spin-orbit coupling effects, and this leads to a description of the magnetic anisotropy, which you can look at by just looking at differences of these energies when the system is magnetized along one direction or it is magnetized along another, or I prefer this method, I think it can be numerically more robust, is to look at the torque. So you're looking at small variation of this energy, you're exploiting the stationary principles of the energy functional, etc. Look at small variations of the energy as you change the magnetization direction to characterize the torque, and from this one can pull out the various anisotropy effects, anisotropy coefficients. Okay, so that's the basis. I've just got in red an aside. I always, just kind of from an undergraduate point of view, I think it's just quite nice to just remind ourselves as to where some of the structure of the Dirac equation comes from. To remember, the Dirac equation now has its solutions which are bispinners, so 4-component systems. So where does this come from? Just for a free electron, if we're thinking of undergraduate quantum mechanics, one says, well, one looks at the classical expression for the energy, in this case relativistic, from relativistic mechanics. So you've got the square of the energy is equal to the momentum squared and velocity of light squared plus the rest mass squared. And then if one's now constructing a quantum mechanics theory, one at least wants to ensure that any Hamiltonian that you put into some wave equation is going to be such that if one operated it twice or squared it, then its eigenvalues would be equivalent to the classical expression, the energy you'd get from the classical expression. And so rather than doing something awful by attempting to square root this expression, one looks for a linear combination in terms of the momentum, operators, the components of the momentum and the rest mass, and then sort of takes this Hamiltonian, operates it twice, and then sees what it takes to get this equivalence. And from that, Dirac's conclusion was you had to make these coefficients 4x4 matrices. And then so from that necessity to just follow the correspondence principle, etc., out pops spin. So I think that's a really nice story. Okay, so what we have then, going back to the relativistic density functional expression, we have this energy with its various terms that should be familiar. Piece from the kinetic energy of this effective single particle term, the Hartree term, the exchange correlation, and then the coupling to the external fields. And then one has these single electron Kohn-Sham-Dirac equations to solve consistently. So here's the form of the Dirac equation, and now we've got both a scalar potential part and also a piece that's describing the magnetic component, at least that's coupling to the spin part of the current. And so one that has this self-consistent loop to carry out. So one, as ever, one guesses a form for these potentials and effective fields, solves this single particle equation, then constructs the charge density from these states and the magnetization from these states, where we're looking at these 4x4 matrices, and then proceeds to consistency. So that's it formally. So what we want to do for this school is to just see how that part of the problem is dealt with scattering theory. I'll do shortly, but just to remind us where spin-orbit coupling comes from. So one looks at this Dirac theory and then takes the leading relativistic effects. Then out comes the leading corrections, mass velocity, Darwin, spin-orbit terms, and coupling to the magnetic field. And this leading terms, one concentrates on the upper two components of this spinner. So this is just a two-component spinner. And one finds the form of the spin-orbit coupling term with the appropriate factor coming from the proper relativistic treatment. And that's the piece that's driving a lot of the physics that I'm going to talk about. This has an influence on the band structure. Here, you can see by its yellowing nature, this is a very one of the very early calculations. This is a calculation by Alan McIntosh, I think, very early on, which just showed a comparison between platinum, dealt with the Schrödinger equation, dealt with the Dirac equation, FCC lattice, etc. So here's the bands from non-relativistic description. One sees basically a free electron like sp band, hybridizing with some more narrow d bands. Now, what the relativistic effects do, so what these terms can be seen to be doing, is that the mass velocity and Darwin terms essentially are shifting down this free electron band with respect to the d bands, and the spin-orbit coupling is then breaking the degeneracy as you can see here. So you've got two states at their gamma point with in non-relativistic description. We've got three bands here, and so this measure of the spin-orbit coupling as to what is this measure of the splitting. So that's a very early calculation. Much more topical now is the consequences of spin-orbit coupling when you're looking at materials which come into this class of topological insulators. So here we've got some degeneracy, and then again spin-orbit coupling is breaking that degeneracy with profound effects. Okay, so now I come on to how basically tackle this solution of this Cohn-Sham-Dirac equation for a system with possibly quite a complexity of potentials and magnetic components here. So to describe the DFT part for a solid. So first part, we want to think about a scattering, a multiple scattering prescription. So one's going to assume that the system can be described as a set of scatterers, and then one calculates the scattering from each scatterer in turn, and then links it up via the multiple scattering formalism. So the first task, if you're setting up a theory of this type or a formalism of this type, is to solve the problem of scattering from a single potential. And I'm going to just concentrate on a case where the potential is spherically symmetric, but it has a magnetic component. And I'm going to say, if it's a single site, I have the freedom to specify the coordinate frame I want, and I'm going to use the direction of this magnetic component to define my z-axis, so that this magnetic component is along the z-axis. Now, we want to we've got some spherical symmetry to exploit, so I'm going to write down the solutions of this Dirac equation as a combination over a quantum number, which I'll come to in a minute, and then there's two in terms of two radial components. So remember, this is a bispinner, so it's 4 components. So there's an upper radial component, which is multiplied by a combination of Pauli spinors. So this is a product of Pauli spinors and spherical harmonics, and they're weighted by appropriate coefficients, namely the Clebsch-Gordan coefficients. So that's the upper component, and then there's the lower component, which is coupled to similar quantities, but with a change in the quantum number that goes alongside it. So that's what we're going to look for. We're going to look for solutions of the Dirac equation of that type. So I've specified what those spin angular functions are. Now, the quantum numbers that are used typically in the literature when you're talking about relativistic quantum mechanics are known as kappa and mu, or I'm going to call it mj. So mj is the z component of the total angular momentum. Kappa is basically a shorthand for both the total angular momentum, so spin plus orbital, and the specific orbital angular momentum. So if one's thinking about adding an angular momentum L to spin of 1/2, then we've got 2 possible values of the total angular momentum, L plus 1/2 and L minus 1/2, and then this kappa labeling, the one with plus 1/2 goes alongside a kappa with a value minus L here, sorry it's not very clear, minus L minus 1, and then for the total, the value of the total, which is L minus 1/2, then that picks up a kappa value of L. So if we're thinking about d electrons with L equals 2, we would have 2 kappa values, minus 2, minus 1, so minus 3 and 2. So that's how the 2 things will be labelled. Now, we've chosen this way of developing the solutions because these spin angular functions are eigen functions of the spin-orbit coupling interaction. So it's that part of that you would expect to see coming in the Dirac equation. These are already eigen functions of that operator. However, we've got this spin polarization piece, and that's going to introduce some coupling between different values of, for any given L, it's going to couple the 2 values of J that it has. So J plus 1/2, sorry, L plus 1/2 or L minus 1/2. Or in other words, with this kappa notation, it's coupling the 2 kappa values that are associated with the given value of L. Okay, just one final piece, just formal. So I've just kept a label here. Nu is just to keep track of the different solutions that that one has from these radial equations that one needs to consider when you're setting the appropriate boundary conditions. So we're going to have solutions, for example, which are regular or irregular at the origin that match some asymptotic, some free electron solution outside the potential, as usual with scattering theory. Okay, so that's the setup, and so one then takes that 4-component wave function, this combination of them, and then looks what is the nature of the radial equations that one has to solve for a single site, and this is what they are. So we have coupled radial equations. So we keep track. You'll be able to have these slides later, so hope you can follow it from the slides. But just to highlight here, so each label is being specified here. We've got the nu, just going to keep track of the different solutions that one can get, and then these different values of kappa. So there's a kappa there that goes through the whole radial equation for this the lower component, And so there's the lower component, and it's coupled to the higher component. And then there's this coupling factor between the different values of kappa. And there's the all-important coupling between two, for a given value of L and an MJ, it's going to produce an effect of coupling from the solution from another radial equation involving kappa primed here. And then the upper component then has this radial equation of this form, which again has a sort of similar structure. And now to complete, so one's got these two equations, and they're going to be coupled to the values involving the kappa primed. So that's what that means. You have basically a set of 4 equations to solve. And then one takes a suitable combination of these solutions to match at the boundary for free electron solutions to then pull out a single site T matrix. And again, this is a very much a couple channel scattering problem. So that means that the T matrix is also off diagonal. And so it's specifying the coupling between a channel that's labeled by kappa, so L and a particular value of L and J, either L plus a half or minus a half, and the other possible value of kappa. So again, L and J plus or minus a half, and it's diagonal in MJ. So that's quite involved, but it's actually not too difficult to set up. Oops, numerically. Oops, gone back the wrong way. So once one's obtained that single site T matrix, then you're in business. You specified the nature of the scattering on a single site with this magnetic component. Okay, you've got the magnetic component along the Z direction, but that's just how you've happened to have specified your coordinate system. So now one can just straightforwardly transform that, or kind of rotate it to describe a situation where the scatter is along some other direction. So one basically just takes the output of some routine that's generating these single site T matrices, and then one rotates it for whatever direction you want to specify that the spin or the magnetization of a scattering site is at any point in your material. So that's the guts of it. It's time. Okay, so now we've got the T matrix, or at least have the methodology to get the T matrix for a given potential with a magnetic component. And now one just feeds that into the formalism, which if I understand you've seen other talks already. So one then notes that we can talk about the scattering from many such scatters of this type by using scattering path operator formalism. So this is where you pick up a description of an outgoing wave from some site J if you've got an incoming wave on another site I. And so we've got scattering, and then these G's are sort of describing the free electron propagation from one site to another. So essentially you've got the scattering T matrices to describe the fundamentals of the potentials, and then the structure constants are just telling you where you have then placed these scatterers. And then one sets about determining the multiple scattering from the system. As ever, one looks for appropriate representation. So I've written it generally here, but for relativistic multiple scattering, these Qs, these labels could be the kappa MJ, so LJ and MJ labels, or equivalently by just considering the transformation from these spin angular functions to spherical harmonics and Pauli spinors, etc. You could express this just as well in terms of orbital angular momentum, it said projection M and the component of spin, so LMS, LM, and MS. Nonetheless, one has whatever representation you choose, one then has to solve this multiple scattering equation. So as I said, the free particle part is specified by the structure constants. And then, if you want to look first off to understand what the band structure is like, formally, one would look at finding the zeros of the KKR determinant. Or usefully, I'll come on to that in a minute. Okay, so calculating properties. Again, this is the same structure as the theory has in the non-relativistic limit. So you base it all on a Green's function, and you can write the Green's function down in terms of the pieces that one's generating from the scattering theory setup. So we've got the scattering path operators, whichever representation you're using, and then we've got these four-component spinners that are coming from our the solving of the single-site problem in the appropriate representation. And so overall then, the Green's function is not a scalar quantity or 2x2 matrix. Formally, for relativistic scattering theory, this would be a 4x4 matrix. So this would be a 4-component column piece and then a row piece for the other side. And so these single-site wave functions are formally, the regular and irregular solutions to the Dirac equation for a single scattering at some position Rn. Actually, yeah, Rn, yeah, with that label. And likewise, yeah, so for regular and irregular. So it depends on how you've matched those combinations of solutions that I talked about earlier. Okay, so that's the formal structure. So that's where all the observables are coming from and how they're constructed out of scattering theory pieces. So from that point, one then can extract out the densities that one would need if you're producing, if you're iterating to convergence in the density functional setup. So you get the charge density by taking now the trace of the Green's function, taking its imaginary part and so forth, and integrating up to the Fermi energy or at finite temperatures using the Fermi-Dirac function, where nu is the chemical potential. And then to get the magnetization, one would also then take a trace of the Pauli matrix. Remember, these are 4x4, so beta is a 4x4 matrix. We've got 1 on the first two diagonals and -1 on the other two diagonals and 0 everywhere else. Sigma, this 4x4 Pauli matrix, or derived from the Pauli matrix, has the Pauli matrix, the regular 2x2 Pauli matrices in the off-diagonal blocks, 2x2 blocks. That's how one would then determine the magnetization, by looking at that matrix, multiplying it by this 4x4 quantity, the Green's function, tracing it, and then taking the rest of the imaginary part and so forth. Okay, so those are the observables. The density of states, similarly, you can extract out by taking some trace of the Green's function, and similarly the spectral function, which I think you've discussed earlier. Again, this part of the structure is exactly the same as in regular non-relativistic theory. Okay, so now I want you to go on to what one can extract out from this setup that one can't get from just a regular non-relativistic description. And so this is my main focus, is to look at magnetic anisotropy effects. So let's say we have a setup where we can sort out the scattering problem for a set of scatterers, and we can feed in what directions their magnetic components are aligned with. And then one could go go ahead and solve the density functional theory for that and extract out the energy, etc. Now, if one really wants to get a handle on the anisotropy effects, then one can just test what's the effect on that energy if you now just vary the angles of those magnetization components by a very small amount. In the limit, you just take the derivative, or essentially the torque of what specifies the torque from this energy expression. Formally, from scattering theory, we can do this in a nice way and get a closed expression for the anisotropy. So one sets up with assuming that we've carried out a self-consistent density functional calculation where the system is now magnetized along a set of directions on the different sites. And then one writes down the form of that energy in terms of scattering quantities, etc. And we've got the single particle part, which I'm not sure if you've seen this already, but so in density functional theory, this would be the sum of the single site energies, and you just sum up until you've used up all the number of electrons in the system. So that'd be sum on E, little e, over all the occupied states. In the scattering theory, this will be an integral of energy and the density of states up to the Fermi energy. So E times little n, the density of states. But one can just then carry out an integration by parts to re-express this expression. So now we've got the total number of electrons one would have in the system, or at least per site, multiplied by the chemical potential of the Fermi energy, minus, now this is this integral of a quantity which is the integrated density of states. So what this is just counting up the number of states that are occupied up to some energy, and then one's then integrating this quantity up to the Fermi energy. And so that's contained essentially all the component, the contribution to the density functional energy that's coming from the single particle energies. Now, I've gone on about that for a specific reason, in that in multiple scattering, this integrated density of states has a particularly neat expression. It's the famous Lloyd formula that specifies it. So it's written in terms of the integrated density of states for free electrons, plus this term, it looks horrible, but it's a log of a determinant of the T matrices defining the system and the structure constants. So if you have a number of sites in the system, then that would specify how big this matrix is going to be. And then you've got also the representation, the angular momentum representation to consider. So this in here is some large matrix, and then one's got to determine its determinant and then log it to end up getting an expression for this integrated density of states. So that's what we're going to start with. It looks complicated, but it actually is rather nice because it's one way you can sort of expand. You can look at small differences and expand this out using properties of logs. So on each side for a system which maybe has magnetic components pointing along different directions, we have different T matrices, which we can set up by solving the single site scattering problem for a magnetic component along the Z direction and then rotating. And then one can feed this into this expression. So we can express this formally in terms of these rotations about an axis which is perpendicular to Z and the direction in which which it's magnetized, and J is the total angular momentum. So now if one looks at just varying this energy, and just by thinking about on any given site, where is the magnetization orientated, and then we're just going to look at a small rotation. We just see the variation of that angle as we rotate about this axis which I've called d hat. So that means we're going to vary this energy with respect to that angle on one side. And because we assume that it's, that we have a self-consistent solution in the DFT already in place, that means we only have to be concerned with the variation on this single site energy term, because there's no going to be, to lowest order, there's going to be no change to the charge density and the magnetization density. It's just changing the direction. And then by using this Lloyd expression and then varying, carrying out this, using this expression for a T matrix, and then basically just looking at the variation of these terms, one gets a closed expression for what the torque is. So it's the scattering path, the diagonal scattering path operator on the site which we're rotating, multiplied by a matrix element involving the T matrix that you're rotating along its original direction, multiplied by a matrix involving the total angular momentum dotted or scalar product with this axis about which you're rotating. And one has to think about the commutator of that. And that's what you deal with. This would be, you get equivalent information if you assumed that the charge and magnetization density magnitudes weren't changing, and you just magnetized the system, the potential on one direction, and looked at another, and then you look at the differences. But this is just looking at that variation. Okay, so that's an expression from the torque, which is available from multiple scattering expression. So let's see now how to apply that. So let me just go back. So one could consider, let's say we have just two scatterers separated by some distance r12, and they have two different orientations. And we're going to just say that these two scatterers are just embedded in some free electron background. So we're going to consider how they interact with each other by using this expression for the energy. So in this case, the integrated density of states would just be involving T matrix of one site, T matrix for the other site, and the information about where they're situated, so namely just from the structure constants which are describing the propagation, free electron propagation from one site to another. So this will be just for two sites. If one goes through this carefully, for the time being, let's just assume we're just dealing with regular non-relativistic scattering. One can show that in the limit where you're pulling these two sites far apart, you're taking the asymptotic limit, you can deduce that the energy of interaction between them has this nice sort of form. It's just the scalar product between the two orientations of the magnetization pieces, and a piece that falls off as 1 on r cubed and oscillates as these two sites are brought further and further apart. And this, you probably recognize this is the form of the famous RKKY interaction. So interaction between two magnetic impurities in a free electron gas. But it's a kind of nice scattering theory application just to see how you can derive this from scattering theory. So now if we carry through the same process now, but assume that the scattering from these single site scatters is dealt with relativistically, so we have to account for the spin-orbit coupling that's going to influence the electron as it gets close to each site, each nucleus. One goes through this, and we can show then that this is now a place where no longer are the spins just concerned with how they're orientated with respect to each other. So we've just got this scalar product here, so S1.S2. But in fact, they also sense how they're orientated with respect to the only direction that you have in this problem, which for this simple two site problem is just the vector that's connecting the two of them. And so formally you can show that the energy now has a dependence on the scalar product of one orientation of one spin with this only spatial vector you have in the problem, R12, multiplied by the same thing with the other spin. And also, if you look at the cross product of the two spins, you find there's also a dependence on what is the scalar product of that with this vector here. So I've written it in that form, and note that it's squared. So this means if I swap S1 with S2 or E1 with E2, I get no overall change of sign. So what this is describing then is an anisotropy, but it's uniaxial anisotropy. So for a two-site problem, that just means if I swap the two spins around, I would get exactly the same result. So it's a kind of simple way to view what a uniaxial anisotropy is. So just proceeding, one can then make this, just explore what else one could get out from it. So let's think about trying to break the symmetry some way. So we can break the symmetry by adding a third impurity. It doesn't have to be magnetic, it can be any scatterer. So just add a third site and then properly use this Lloyd expression for the integrated density of states, construct the energy, look at the energy of interaction between the two sites, and one can find then that there's a unidirectional anisotropy that drops out. In fact, it's of the Dzhalazinski-Maria type. So this would now say it would matter very much if you swapped E1 and E2 around. So it's a kind of way of picking up that it's a unidirectional anisotropy. So it's just nice sort of examples that you can run through just to see how scattering theory works when trying to get out interactions between sites which you're characterizing by some magnetic component. Time, okay. Crack on. So let me now just show some work which I've reproduced from Hubert Nyan's and Dimo's very nice review article, which now shows an application of this formalism now to a much more realistic system, which has basically small nanoclusters of magnetic atoms deposited on some substrate. And the picture up here is actually chromium, magnetic chromium atoms deposited on a gold substrate. And then what was done in this work was to explore how the interactions depend on the spatial locations of the atoms. And then what they did, or what we did, was to then analyze these energies for these different configurations and how they're orientated and so forth, and we could fit a kind of little spin Hamiltonian from them, and we can pull out an isotropic Heisenberg-like interaction between between all the pairs of spins, a piece that is anisotropic but is symmetric. So if you swap these, won't get any change of sign or anything. And then the Dzhalazinski-Maria type interaction, which is now unidirectional, and then some single site anisotropy term as well. And so one can then characterize these sorts of clusters, just shown here for just three, in terms like so. And can extract out these Dzhalazinski-Maria type interactions and so forth. On the bottom, I show some work from Manuel dos Santos Dias did me and Laszlo Sonyua and colleagues a few years ago now, where he looked at it's the same sort of formalism, but he was looking at putting a monolayer, a manganese monolayer on an FCC substrate. He looked at several silver, gold, platinum, etc. And we could deduce the circumstances in which these chiral patterns would be the ground state structures. So it's all from this formalism. Scattering theory, looking at the energy of interactions by looking at the Lloyd determinant and so forth. Okay, that's the time. Okay. Right, so that's the first part. So I thought just for the last sort of probably finish a little bit early, but for the last 20 minutes or so, probably 20 minutes or so, I'll just talk about how we can use this sort of setup to look at actual effects on real magnetic materials when their temperature is changing, and also, in principle, when you're applying some external stimuli. So applying external magnetic field or a pressure or strain or whatever. And so the motivation for this is want to understand what drives a magnetic phase transition, and indeed whether it's a discontinuous or a continuous phase transition, it's first or second order. This uses in solid state refrigeration, but some of the other aspects will be important in understanding how a magnet retains its hard magnet properties to high temperatures. This is quite a big deal for applications of permanent magnets. So with this brand of materials modelling, where we're including the formal consequences of spin-orbit coupling and spin polarization onto the properties of the electrons in materials, one attempts to pull out parameters for further modelling of these materials. That's what I'm going to talk about a bit now. And as ever, one has to work very closely with the experiment to get some insight. And hopefully the output will be some robust way of determining parameters for longer length scale modelling. Okay, so again, we know what the challenge is for if we're trying to carry this out. So we've got to deal with all the many interacting electrons and nuclei, and many body quantum mechanics. Excuse me. That I've already talked about. That we start off with density functional theory, relativistic density functional theory. Now, if we add on top of that variation of temperature. So what's the type of things that we're going to have to bother about? Well, we could say we just need to develop a more exotic or a more rich exchange correlation functional, and that would contain all these finite temperature effects. But that's very hard. So one instead just thinks back to what the physics is. So we know as material is heated up, in the interacting electrons, there's going to be some, at low temperatures, there's going to be some collective modes that are excited. What we want to do is then, of all these collective modes from the electrons, see if we can spot those that are relatively slowly varying compared to other ones. So if we think about electrons and nuclei, then this is quite obvious. We know that the nuclear vibrations are happening on a much slower time scale than the electronic degrees of freedom. So typically, one makes the Born-Oppenheimer approximation and makes the separation. But now if we fix on purely looking at the interacting electrons themselves, are there some degrees of freedom which are relatively slowly varying compared to everything else? And we kind of set up a theory based on that. So we know that spin waves are excited at relatively low temperatures in magnets. And so for a ferromagnet, you have these sorts of spin wave modes. And then if one just assumes that these sort of excitations prevail, and the material is heated up, the interactions among these spin waves produce some description where if you took a snapshot of the material, then you'd see the magnetic components being frozen along different directions. And if one waited a short time later, then these would have moved to be pointing along some different directions. So you've got these configurations, these local moment configurations, which are just, you're assuming, are relatively slowly fluctuating in comparison to all the other electronic degrees of freedom in the system. So that's the essence of what people are doing when they attempt to extract out spin models from descriptions of metallic materials. So that's the idea. So from the idea is that a magnetic material, with all its many electrons and its nuclei arranged in particular ways, can be characterized at a finite temperature by saying that it has atoms, which and then the electronic density near any atom has a magnetization direction along a particular direction, and then at a time later this will vary and point in a different direction. So we've got these fluctuating local moments. But meanwhile, while that variation, that change in direction is happening, the electrons are scattering on and off at much faster timescales to essentially sustain those local magnetizations. Okay, so for more details about that, you can see Jürgen Kubler's excellent book as well as some other review articles. Okay, so that's the idea then, is to say that we could, from a density functional prescription, we could constrain our system to have magnetization directions along a bunch of orientations, so a bunch of little unit vectors. Then one would visualize those as being classical spins, and then carry out the statistical mechanics of those by averaging over their properties thermally. So you're basically making this timescale separation to extract out these slowly varying degrees of freedom and then deal with their statistical mechanics. So that's really put in a nutshell here in this block here. So as I said, you constrain the system to have some non-collinear spin polarization. So that sets up some energy as a function of these constraints, and then one can apply an external magnetic field or strain it or apply pressure or whatever. Then, formally, one would then have to think about how to carry out these averages of the configurations with the appropriate probabilities, appropriate Boltzmann weights, and what can be done. One powerful way of doing this is to use techniques which can be adapted from how you deal with compositional disorder in alloys. And you can couple it with models of lattice vibrations, or indeed, as Hubert Ebert's group have done, also deal with the disorder of the nuclear vibrations with techniques adapted from disordered alloys. So this is in essence describing the disordered local moment theory of how to describe magnetic properties as a function of temperature. So one looks at the average of these energies as a function of temperature, and sees what's the order parameter, how the order parameter varies. This average, how the average varies as a function of temperature. And of course, at low temperatures, be complete order. At high temperatures, there would be an equal chance on any side of these moments pointing in any direction, and the system would be overall paramagnetic. Okay, so that's the basis to it, and I will show a few results from a recent project on rare earth transition metal permanent magnets. A lot of interest in this. Many magnets in materials and applications and devices are composed of, or in this famous neodymium iron boron family. Neodymium 2 iron 14 boron. So it's a lot of iron, still quite a lot of rare earth. Now, because of the rare earth, they have these magnets have high anisotropy, so that means they're good permanent magnets. Unfortunately, however, this anisotropy effect, which I'm not going into here, into today, it can be shown from these disordered local moment theories and also much earlier theories, single ion anisotropy theories. It can be shown that it falls off quite rapidly as a function of temperature. So as the magnetic order diminishes, then the anisotropy actually diminishes at a faster rate. So this has real like consequences for these magnets. So that means these nice stable neodymium iron boron magnets end up having their hard magnetic properties actually fall off quite rapidly with temperature. And a way around that is to mitigate that is by adding some other rare earth, and typically that's dysprosium, or trying to put other additives in. And so there's quite a lot of effort now to try to produce magnets with smaller amounts of rare earths, because obviously critical materials and expensive and so forth. That's retain the large magnetic properties, the large magnetic anisotropy to high temperatures. Anyway, so the first thing to do if you want to understand all that is to try to get a handle on where the anisotropy and where the magnetization comes from in a magnet which is involving a rare earth and a transition metal. So this is kind of a rich problem. You've got the strong correlated localized 4f electrons to deal with for the rare earth, and you've got to understand the itinerant 3d electrons of the transition metal, which is going to keep hopefully the magnetic properties, the magnetic order to high temperatures, so high Curie temperature, etc. And you've got to deal with the interaction between them. So the project I've been involved with, we started out by tackling one of the classes of permanent magnets, which has the simplest crystal structure, just to try to pull out some of the principal physics ideas from it. So these are the rare earth cobalt-5 magnets. So there's sort of layers of cobalt, hexagonal layers of cobalt, and then interleaved with hexagonal layers of rare earth and cobalt. So that's why you have this 1:5 ratio. And so, as I say, we've got to the strongest magnet in this class is samarium cobalt 5. But in this project, we want to build it up in stages. So we've got these various aspects to deal with. So the first thing we thought we would handle the itinerant electron component. So we would look at something which is chemically very similar to a rare earth, to an lanthanide, so another rare earth, yttrium, but it has no F electrons. So we would look at the disordered local moment theory for that. Then the next stage up, we'd then look at a lanthanide cobalt-5 magnet, but now it's gadolinium. So gadolinium is a very nice lanthanide to look at, first off, if one's trying to tackle the strong correlated localized F electron physics. Because it has a half-filled F band, that means its angular momentum L is 0, that means its crystal field effects are very small. So you've got essentially the consequences of having localized F electrons and how they're interacting with the itinerant D electrons, but you haven't got any of the baggage that's coming along from the interactions with the crystal field. So that's what we did first off, was to look at what happens to the magnetic order as a function of temperature in well, we did both, but the gadolinium cobalt-5 is the interesting one here. So what we found, and it's consistent with the experiment, in that the order associated with the gadolinium sites decays at a faster rate in terms of temperature than that on the cobalt. So that's consistent with you expecting the cobalt sites to set the magnitude of the transition temperature. So you can see this is the order parameter on the gadolinium sites, and here's the order parameter on the cobalt sites. These are ferrimagnetically coupled, so the ferromagnetic, the magnetization on the F electron sites, the gadolinium sites, is anti-parallel to that on the cobalt sites. So with this nature of how the order decays as a function of temperature, the overall magnetization has this peak at a finite temperature, which is found in the experiment. So that was the first nice thing that dropped out of the theory. So you've got the interaction. We felt we had the interaction between the rare earth and the transition metal fairly well characterized. And again, our transition temperature was in reasonable agreement with the experiment. Next stage up was to see how we could deal with the complicated F-electron strong correlations for these other more appropriate, more relevant rare earth lanthanide metals, so neodymium, samarium, and so forth. So essentially, we've got a description of the gadolinium variant of the class, and now what we are proposing is to then add to that the contribution to the anisotropy from a single ion model. So remember, way back at the beginning of the talk, I talked about the crystal field effects and the dominant contribution to the anisotropy for a material with a rare earth. So what we need then is a very accurate description of the charge density surrounding the rare earth. And so for this case, bearing in mind that the chemical similarity between yttrium and its lanthanide counterparts, we carried out we carried out an accurate description of yttrium cobalt 5, an accurate description of its charge density, from which we could then set up or describe the crystal field for the system, or approximate the crystal field of the system. And then from that, and then the F-electron wave, the localized F-electron wave functions associated with the relevant rare earth, we could then calculate in I think a fairly robust way the single ion anisotropy contributions to describe a system. And that's what we did, and then we ran through. So basically, we ran a series of calculations: yttrium cobalt 5, gadolinium cobalt 5, and then finally this single ion anisotropy contribution added to the rest. And from that, we could then model the whole class of these 1,5 magnets. And so we could determine the magnetization as a function of element and its TC compared with the experiment, and also, but more importantly, the anisotropy. So here is the calculated anisotropy we got from this model and the experimental values. So let me just point out a few features. So so there's the samarium is the winner, as we found. We found we're overestimating the cerium. Cerium has still quite a sizable value, and the rest are fairly well described. Okay, right. So I'm just going to finish up in the last few minutes. So there should be some time for questions, perhaps. So summary. So what I've started with to motivate the discussion was just a mention of the elements, the aspects that need to feed into a description of a magnet. So in terms of exchange, magnetic anisotropy, interaction between applied field and the magnetostatic parts. And formally, if you want to get at this ab initio, then we'd start from a relativistic density functional prescription. This contains all the spin-orbit coupling and spin polarization of electrons naturally. And then what I've outlined is the formalism for implementing this density functional part, at least solving the single electron part with the relativistic multiple scattering theory. One of the nice outputs of this theory is that it gives a nice clean expressions to use to derive interactions between sites which you've designated to have magnetic components along different directions. So you've sort of designated them as spins. And by varying the geometry and so forth, and the nature of the scatterers, one can then explore various types of interactions. And lots of very nice work around on this topic. So you can see that sometimes you have interactions that Zhalezinski Maria-like, which can feed into understanding skyrmion lattices and so forth. From my point of view, I've spending some time in combining this formalism with now dealing with the statistical mechanics of these local moments. So these spins that we've identified as being slowly moving in the glue of all the other electrons. And then looking at the statistical mechanics of those, what is the influence of their disorder on these properties, the interactions and the anisotropy. And so from then, the hope is then to contribute reliable parameters for this longer length scale modeling of magnets. And so this is actually, there's more detail about this project on this website, Pretamag. Okay, so let me just give some acknowledges before I end, and then I've just put down a few references as well. On this last part on the finite temperature properties of permanent magnets, this is a project based originally at Warwick. It's involved, very much grateful to Chris Patrick, who's now in Oxford, Eduardo Mendy-Tapia, who's the cusp of moving from Düsseldorf to Jülich, and Juba, also at Jülich, and colleagues also at Warwick. And I'd like to acknowledge many discussions and work and so on with of colleagues in the multiple scattering community, and I've just put down a few here, including Hubert and Jan. Some references that people might find useful, hopefully. There's the original paper by Rajagopal on relativistic density functional theory. There was a very nice article by Janssen in PhysRev that gives a very nice description of where the various terms that you can then connect to these more long-range models from the density functional prescription. There's Jürgen Kubler's excellent book, review article myself. There's Paul Strange's textbook on relativistic quantum mechanics, which is it's very useful reference. DFT in general, and of course Martin's book. Textbooks, one I particularly found useful. And of course there's Jan and Hubert and Dimo's review article, which is very good as well. For rare earth magnetism and crystal fields, there's lots in the literature, but I've just put down ones that I found particularly useful. And if you're interested in magnetic anisotropy and magnetic interactions, then certainly Sven Bornmann's thesis is good, and papers by Sergei and others. And also more information about the finite temperature effects on magnetic properties can be found in Chris and my paper. Okay, I think that brings me to the end. So there might be some time for questions, or I guess you've got time to go to lunch.
So,
Okay. Shall I stop sharing?
well, you can share it still. Thanks, Julie. So, are there some questions? Could you come here? Sorry, Julie, there. Yeah. You need to...
Yeah.
So, like this, something like that.
I see. Oh, there's a...
Yeah, hello. Yeah, so my question is actually related to the. So you showed something about the direction of the local magnetization on a certain site. So is this direction fixed? Is this like just an input parameter? Like
yeah, at single site level, of course, you're free to choose, right?
right, yeah. So but you cannot really determine the direction self-consistently. So one really has to do it. Like
Yeah, formally, you're absolutely right. So formally what one, if you're saying, oh, I want to look at a system where I've got these magnetic components along a set of directions, then if you're coming at it from a density functional point of view, that means you have to incorporate some constraints to force those spins to be along those directions. And so one should formally account for those constraints. Does that answer the question?
Yes.
So one would do the density functional minimization under those constraints that you are forcing this spin configuration.
But it would be also possible, like within this whole theory, to really determine the minimum energy direction.
Oh, sure, yeah. Then you can explore the minimum. From this finite temperature point of view, formally we're using this constraint idea to look at these configurations under these constraints, and then we're carrying out the statistical mechanical averaging over them to see what is the overall order parameter and how that varies as a function of temperature, to see what is the appropriate nature of the magnetic state as a function of temperature. But the input is then always these energies of these configurations. If that makes sense. I hope so.
Thanks.
I really be good to have a whiteboard, but
Yeah.
talk to you face to face. But here we go.
Okay, some other questions? Sally? Julie, there is a chat message. Could you please have a look?
I'll stop sharing then, shall I? Because I can't see the chat. Oh, wait a minute.
Oh, so I will.
Oh, hold on, I should be able to see the chat.
Can you see it?
Uh,
So there is a question. Is there any way to consider
oh, yeah. Okay, that's
magnetic dipole-dipole interactions in multiple scattering?
yeah, that's a very good question actually, and I'm sure there's many people in the audience who can answer this. What one can do, so if you write down that expression for the magnetic dipole-dipole interaction, and then you put write that down, and then look at the structure constants from multiple scattering theory, and then look at the structure constants when you're taking the energy in your free electron propagation to zero, and you'll see that actually for one of the higher L components, that's the same as the dipole-dipole interaction you need. So basically, you can basically thieve from a scattering theory code to get the pieces out that you would need to get the dipole-dipole interactions. So essentially, you're looking at, I think somebody helped me, somebody who's done this. You need the L equals 2 components of the structure constants, or something like that, isn't it? And you evaluate it close to energy 0, and you gain ability to get this dipole-dipole contribution out. So yes, there is a way to get the dipole-dipole interactions.
Okay, thanks. Yeah, sure, come.
Julie, sorry for adding some information. So maybe you have forgotten that paper with Sven Bornemann we had on that problem. So we included the bright interactions, the Hamiltonian.
Yes, true.
And
Yes,
so on that basis, you have it in from the very beginning.
Absolutely, yes.
Yeah.
Yes, you're absolutely right. I should have mentioned that. Yes, formally, of course, you're right. You take the bright interaction and take the classical version of that. Yes.
Okay.
I was just thinking practically as to how one sets about actually calculating it. Yeah, but you're absolutely right. Thanks, you. But yeah.
Thanks. So Salim, you have started?
Yeah, hello ma'am.
Hi.
I need your expert opinion. In the last slide, magnetocrystalline anisotropy, there is overestimation for I think for one system. I also have experience with iron platinum, and it's sensitive quantity.
Sorry, which system? Iron platinum.
Iron platinum, I have experience with that.
Yeah.
So there is
Yeah.
always like overestimation, though we check several convergence parameter. So I need your opinion that whether it's because of the proximity or nature of the DFT, or there is always like small disorder present in the experimental sample. So I just need your opinion.
So the calculation you've done is for bulk iron platinum, is it?
Yeah, it's iron platinum.
Okay, so a perfect L10 structure,
Yep.
and then you're carrying out DFT, relativistic DFT to get
Yeah,
out
we
the
check
anisotropy.
like multi-code approach. It's already published. So
Okay.
yeah, like the theoretical data like agree fine
Yeah.
enough, but with experiment it's overestimated. So this is just question that whether it's like there is always small disorder present in the experimental sample, or it's because of the proximity or nature of the DFT.
I think it's a mixture of both. I don't know which experiments you were comparing with, but I know at this level of DFT, if you want to, you have to compare with sort of single crystals, and you have to bear in mind that the shape of the crystals as well. So you have to incorporate the shape anisotropy. But I think for iron platinum, you're overestimating it. If you're comparing the experiment, at what temperature have they carried out the measurements? Because the anisotropy falls off, as I said, quite rapidly. It falls off the order parameter squared in iron platinum experimentally. So you need to know exactly what temperature you're at. You want to look at the T=0 temperature, or close to T0 as possible for your DFT comparison.
Yeah. Okay. Yeah. Great.
Okay, thanks, Julie. So Salim can maybe, if he has a more
I can
detailed
write.
question, he can write.
Yeah,
it
yeah,
down.
I looked at iron platinum probably too much in the past, so I don't know quite a lot about it.
Okay, so thanks, Julie, and because we have to go for lunch now, so thanks a lot, and
Okay,
I hope
cheers, yeah.
we will see you soon.
Cheers, then, bye.